Hi class, this video is to provide you with detailed information on 215-211 Mechanical Engineering Project 1. So this project, as you all know, is for designing a beverage cup warmer. And the design goals includes two steps or two targets. One is the energy efficiency and the other is the temperature control. Okay, so maintaining temperature. So you're trying to design a cup warmer that will efficiently heat the beverage in a cup and maintain the temperature between 54 to 56 degrees C in an ambient or room condition of 25 degrees C. That's the simple and the overall goal of this project. Okay. Now, if you search for beverage warmers or coffee cup warmers in the internet, this is the type of warmers that you will find. And you can see all of them are like a flat hot plate design where you take your beverage cup, hot beverage cup, and you place it on it, and you either connect it to a power supply or it has a battery that's already charged and you turn it on. And the manufacturers claim that they will control your temperatures to a certain within a certain spec. Okay, some of them even let you select the temperatures you want. But this is the most common design, and the reason for this design is it allows you to put any diameter or any shape of cup on a flat surface. Okay, but as you can see, all the heat and the temperature sensing is on this particular hot plate. So all the heat losses can happen from the top and the side of the cup. So because of that, to account for that, they have to use very high power heater. Okay, we want to limit the amount of heater that we are using in this class, and because of that that being one of the reasons, your design will be something like this. Okay, your design will be limited to certain cup sizes and you'll be using a lower wattage heater close to 9 watts. So you will basically have an insulated warmer. These are not insulated, they are exposed to ambient. Okay, so you'll have an insulated warmer. That will mean that you can potentially use less than 9 watts of heater power and turn on and off and maintain the temperatures. Now, what are the components that you need on the warmer? So the cross-sectional view on this right side gives you some details on the components needed. You will have one thermistor for measuring the temperature of the cup or the beverage in the cup. Specifically, we are looking at the center temperature, okay? But you cannot directly measure that. You have to indirectly measure it by putting the thermistor on the cup warmer. Then you have to have some kind of barrier. You could use, in your case, you could use some kind of aluminum foil, for example, an aluminum tape that separates the thermistor from the cup, okay? And then you have heaters that are coiled around um, for heating the cup, and then the insulation surrounds everything else. Okay. Now, one thing to note here is, of course, you can have the thermistor at any location. You could have it here, here, anywhere. The heater, you could coil it around anywhere. You could have the heater on the bottom. Both the thermistor and the heater are in the bottom. All of those are your choices. Okay, but you need to have a heater, and that particular heater that we will provide will be close to 9 watts. Okay, and it will be a 12-volt DC heater. Um, there will be LEDs for status indication, um, for indicating whether the heater is on or off and whether the temperature is within the control specs or not. Okay, and the thermal insulation material is something that you choose. Metal foil barrier, you can design whichever way you want. The reason for the metal foil barrier um, is, of course, to provide good thermal contact. But if you look at all these designs, you don't see any heater sticking out or a temperature sensor sticking out, right? They are isolated from the cup. So the same way you have to design such that none of that hits your cup. Okay, when we look at your warmer, you shouldn't be able to see any heater or the thermistor. You should have everything covered with either a metal film or a barrier or a foil, um, and that will provide the thermal contact needed for heating and temperature sensing. Now, for the control system components, the things that will control the heater, measure temperature, change the LED status, all that, what you'll have is Arduino boards, relay shields, thermistors, LEDs, DC power supplies, and DC heater cables. Okay. All the control circuitry should be inside a control box and adjacent to the warmer. And this should be very portable. Okay. You should be able to move it without a loose connection or something not working, all that. So make sure that you make it a really robust design. The following hardware sets will be provided, and these include the Arduino board, one board per each team, two thermistors, NTC thermistors per each team. NTC means negative temperature coefficient. You have 10K ohm resistors for use with the thermistors, and you have 220 ohm resistors for use with the um, the LEDs. Okay. Then you have the 12 volt DC power adapter, which will help power the heater over here. You have relay board for use with the Arduino for turning off the heater, turning off and on the heater. You'll also get a plastic cup for your practice, and for the final exam, use the same cup. Okay, use this to build your um, setup and also bring it to the final exam. Heater wires, uh, unfortunately, we couldn't find the right resistance. So what we do is we give you four heater wires of 59, roughly 59.5 ohm each that you have to connect in parallel. Okay, and before the test, we'll measure the resistance. Now, some of the design constraint. The first constraint is the dimensions. So you shouldn't have a diameter or the outside diameter of your cup warmer more than 11 centimeters. Okay, it should be less than or equal to 11, less than or equal to 11 centimeters. And the height, overall height of your cup warmer should be less than or equal to 8 centimeters. Okay. Um, then the other constraint is, um, like we already discussed, no direct contact between cup and heater wires or thermistor. So you have to use a barrier for heat conduction and thermistor sensing. You cannot use any additional heat sources other than the heater provided, and use the 12 volt power supply is the same power supply provided. Okay. Um, the control box with Arduino board and other circuitry, and you can use any plastic box and make sure you put everything inside uh, in a organized way. And other circuitry should be portable and have a minimum cable length of 1.5 meters from the warmer. And this will help make the final test go smoother when we have to test several teams uh, setups together. Okay. And the LED status indication should be installed outside the warmer, adjacent to the warmer, for easy visual inspection. Um, as you saw in the previous slide, one of the previous slides, I had put the LED warmer here. You don't have to put it there. You can put it somewhere here. You could even put it next to the warmer somewhere here, you know, the two LEDs. Um, but it should be very close to the warmer that we can see. Okay. So the beverage cup was provided to you. It is not exactly same diameter from top to bottom, but the diameter in the top is roughly close to 7 centimeters, and the height is close to 10.3. Okay, this is H times D, and roughly the volume is 350. Um, and the material is this. So you should measure your cups yourself and get the dimensions accurately, um, and that you could use to do CAD designs of your beverage holder, which you can then machine out of the right material to create the final cup holder. So this slide shows the project deliverables. For midterm, you have a classroom demonstration, which where you have to show the thermistor calibration capability and your LED status um, control. And afterwards, you'll have a midterm presentation. Um, then for final exam, you'll have three sections. One is the temperature control performance, which is a classroom demonstration, followed right immediately by thermal efficiency test, which is also a classroom demonstration. And then there will be a final project report and a project presentation after the classroom demonstrations. Not the same day, maybe a few weeks after that. So let's look into the midterm examination goal first. Um, Goal number one, which is the classroom demonstration. So in this case, we are trying to look at how good your thermistor calibration is and how is your control algorithm working based on the thermistor measurements, and you have to show that based on turning on or off an LED. Okay. The goal of the thermistor calibration is when a manufacturer makes a thermistor and says that okay, it has this following specs, it should read this. Um, the 100 thermistors that they make, that doesn't mean all 100 of them will measure the same temperatures. So there will be some errors here or there, and there will be errors in your setup in the way you have connected it. The secondary or third resistor that you're using, maybe that has a small error. So all of that has to be accounted for and cleaned up and make sure that your thermostat is reading actual accurate temperature. So that's what the goal of the midterm examination is, or one of the goals. Okay. So we will test your thermostat at three different conditions, and the first one will be um, close to uh, a close to 32 degrees C when you're holding the thermistor in the hand. Okay, so somewhere between 30 to 33 C when you're holding it in your hand, and then you have to be able to measure 0 degrees C when it's in an ice bath, where ice is partially melting. Okay, and then it should also um, um, read very close to the room temperature, which will be um, what we'll do is we'll have water at room temperature and we'll measure the thermistor is reading that water temperature correctly. Okay, so three different temperatures, 1, 2, and 3. So all of this will be compared with the reference um, sensor, and how much your temperature deviates from that reference sensor will show the performance, okay, of your calibration, or the accuracy of your calibration. And then your LED is supposed to turn on when it's less than 1 degree C or when it's between 30 and 33 degrees C. So when it's in the hand, when somebody's holding the thermistor in the hand, then the LED should turn on. And when it's put in an ice bath, it should turn on also. Every other condition, it should be off. Okay, so that's the goal of the classroom demonstration. The setup for the classroom demonstration looks something like this. These are all the components that you need. Um, all of these were provided. And then it's best if you can have roughly 1.5 meters long cables starting from your Arduino. Okay, you don't really need a control box for this test, but for the final test, you should have everything secured in a control box. And then only the cup warmer should be outside the control box. Okay. What is expected from your computer is in the serial monitor while we are running the test, you should be able to output the temperatures and also the LED status. And of course, yes, you can see the LED status should be on when the temperature is in between 30 to in the range of 30 to 33 C. Okay. Um, and if it's outside of that, it's off. And if it's less than zero, it should be on again. Okay, here, or less than 1 degree C. Sorry. How do we now more details on how to connect a thermistor to the Arduino, and this kind of shows you how to do that. You can see that there is a resistor that is needed, and you are creating a voltage divider circuit. You should try to figure out why thermistor is not directly connected to Arduino and is directly measuring the resistance change. Instead, it is looking at a voltage divider circuit and finding the delta voltage based of that voltage divider. Um, so you should be able to look into the internet and find out why it's done that way. But typically, when you use a thermistor, you use the same resistance as the thermistor's resistance under standard conditions. Okay. You can also see that one end is connected to A naught. A naught is the analog in pin, and the other end is connected to the 5 volts, right? Um, so one end is connected to the black, which is ground, and the other end is connected to A naught and the source supply. Okay. So think about all that, why the connection is that way, and what exactly A naught means, and things like that. So this doesn't show how to connect the LEDs. That's something that it should be easy to figure out. Now, why do we do an NTC calibration? Like I mentioned, um, every single thermistor from the supplier will have some small deviation from what it's actually supposed to do. So we have to make sure that we recalibrate it or calibrate it such that it's measuring the temperatures accurately. First of all, when we use a NTC thermistor, it means it has a negative temperature coefficient. Okay. Um, so what that means is the change in the resistance as the temperature increases is in the negative direction. It decreases. And it's actually not linear, it is logarithmic, as you can see from this chart. So so you cannot calculate the calibration values by assuming linearity. It is logarithmic, and you can use two different equations. One is a simplified Steinhart-Hart equation, also called as beta equation. The other is the full Steinhart-Hart equation. You can use either of them and try to find out what is the actual curve. Okay, so if you have the wrong parameters and you choose the wrong parameter here, for example, the wrong B, your curve might look like this from the actual curve, right? So you want to make sure that your curve is correct and it's measuring the right temperatures. So this relationship between resistance and temperature uh, for the simplified equation is through this value called beta. Okay, so if your values are not correct, if you're trying to read a temperature that you know and your values are not correct, then adjust this B value and try again. Okay, so you'll calibrate this particular sensor using this particular equation by changing the B value. The the sensor that was provided in the class, the manufacturer claims that the value of beta is 3950. Of course, it may not be 100% accurate. Maybe it's 3850. You have to figure that out. How much variation is there, right? It could be 3970. So you don't know the exact value, whether it's provided by the manufacturer is correct or not. So you have to test it, recalibrate it, update this value. And the T naught and R naught values are typically provided by the manufacturer, and usually it will be close to room temperature. In this case, also the manufacturer is saying its T naught is this, okay, and the R naught value is, of course, it's a 10K resistor, 10K ohm resistor, so a thermistor. So that's the value that they're saying it has under standard conditions. Now, the full Steinhardt equation, you have to adjust three values, A, B, and C. You have to find three values. So in this case, you need only one reference temperature and probably can find the B value. Okay. So you have temperature, one particular value of T will give you the correct value of B. If you use two, you could probably average it and get a better value of B. Here, to get one single value for A, B, and C, you need at least three temperature tests. Okay, because three unknowns and one equation. So you need three unknowns and three equations. So you have to have three temperatures, and you get A, B, and C values. Okay. The third one option typically is the manufacturer gives you a full table for an individual sensor, and usually they are pretty accurate that way. But for this project, I would strongly recommend you use this method, okay? And try three different temperatures and find ABC values. Now, what are those three temperatures that you can use? One of them is the ice bath, 0 degrees C, and the other is the boiling water. And then the third one is you can put your thermistor in a water and compare it to a reference sensor in water, and let if the water temperature is stabilized, you could use that temperature as the third temperature. Okay. So if you leave the water in the room, after some time the water temperature will stabilize and you can measure it using a reference calibrated sensor, which is accurate, and use that value as your uh, third temperature value. One thing to note here is sometimes when you take ice from the fridge, ice could be as cold as minus 18 degrees C. Your freezer is minus 18 degrees C or colder. Okay, so that's how cold the freezer has to be to prevent bacterial and microbial growth. Freezer is not at 0 degrees C. Freezer is much colder than 0 degrees C. So if you take ice, it won't melt right away. It will stay solid for a while and it'll cool slowly. And then once it starts melting, then you have gotten close to 0 degrees C. So what you should do is get the ice and make ice bath by mixing some water, keep on stirring, and until temperature stabilizes to 0 degrees C. Okay. And make sure your water is not salty water or dirty water. The ice is also made out of pure water, so that the melting point is not changed. Okay, if you have impure water, your melting point may be lower than this. It could be less than 0 degrees C. So you want to make sure you use clean, pure water for ice and the water that you're adding here. The boiling water, of course, everybody knows it's at 100 degrees C. So boil in one pan and you do the test that way. All right. Now, what are some of the equations that you'll need? Um, so you're basically measuring the uh, resistance, converting that into voltage, and converting the voltage back to, um, sorry, you're basically measuring the voltage, converting that to resistance, and then converting that to temperature. Okay. So what you're measuring basically is this value that is coming out of your thermistor. And this is basically maybe 5 volts that your Arduino is providing to the thermistor. Okay, and ADC max value for your Arduino is typically 1023. What do you mean by ADC is the analog to digital converter. Okay, you should read on what exactly that is. And some of them may have better resolution um, than the 1024 resolution. So in this case, the max value that it can take is 1023. And ADC value is the value you measure at A0, which is the analog input location where you have connected your thermistor. So based on this, you know what is the output voltage. Okay, it will always be less than the 5 volts that you're providing here. Once you know the output voltage and you know the resistor that you have, um, um, the fixed resistor, which is a 10k ohm resistor that you have connected, um, and then so that is 10k, and you also know the V in, which is 5 volts. So once you measure this, you can find the resistance of your thermistor. Okay, this is the resistance of your thermistor. Once you know the thermistor's resistance, you can use the Steinhardt equation. So this R is that R thermistor. You can use the Steinhardt equation using the R naught T naught B and get the temperature T, which is in Kelvin. You could also use this equation and convert the resistance to temperature um, using this equation. Okay, so those are the equations that you need for creating your thermistor logic, and the following equations or following relationships for creating the LED logic. Okay, and you can create a sample code like this using the beta equation. You can see that I've used an ADC resolution of 1023. My nominal resistance is 10,000, and which is basically the R naught, and this is the B or beta, and this is um, the R fixed, the fixed resistor that I had in there, and then this is the T naught. Okay, so you know you have R naught, T naught, RF, and somewhere in here is the V in, which is the 5 volts that we are providing. Okay, so using this, you can see I've used the beta equation here um, for the temperature, and and then the LED logic here. I also used a 1 second delay so that it doesn't continuously type the data into the serial monitor. Okay, so the serial print is what is printing it into the serial monitor. Okay, so these are the formula for you to see it in the serial monitor. The same thing with the full Steinhardt equation. Um, I've changed the equation here to this. In this case, we have three coefficients. These are randomly generated numbers. Of course, this doesn't mean anything. You have to fix your numbers correctly based on tests. And then again, the other values are in here. So very simple to create this code. So the midterm is much easy. Um, the final exam is going to be a little bit harder. All right. So when you finish your midterm, there are some questions you should think about. A lot more questions so that you learn something out of this, right? One was, why do we have to calibrate the thermistor? Okay. What reference temperatures should we use for calibration? Uh, you have connected your LEDs to the digital pins, right? If you look at um, your circuit, you will go back and look at your circuit. You would have looked up online, found something in the web. You would have connected the LED to the digital circuit and connected the output of the thermistor to the analog, right? What are all these circuits? What are all these pins doing? What's the difference between that digital and analog? And uh, what is basically ADC? What is this analog to digital converter? Um, and what is the resolution? Okay. Um, what other capabilities does Arduino have? Um, and why do we need resistors for LED, and why do we need resistors for thermistor? Okay, there are several questions that you should think about, which will make you more uh, uh, which will provide you more expertise with your next Arduino projects. Okay, so you learn certain things by asking some questions like this. All right, the midterm exam presentation involves the following. Um, so what we are looking for is your understanding of the methodology that you're planning to use to prepare for the final exam. So that's what you're presenting. And you can explain it based on simple theory. Even if you don't show any calculations, that's fine. If you explain it based on simple theory on why you have to do what you're doing in all these steps here, that should be good enough. You could also supplement it with some calculations, simulations, or some trial experiments that you have done um, that tells you that, oh, I should do it this way. All right, so what's the first challenge? The first challenge is, what material should you select for the warmer? So there are so many different materials you should select. Of course, there's no point selecting this to be of a very highly conductive metal, right? Then you lose all the heat directly to outside. So you want to trap the heat inside. So you want a good resistance material. You also want something that you can machine down easily, such that it could be machined in a CNC uh, or in the workshop at the mechanical engineering department. So you want something that's easily machinable. Um, and uh, Insulation, machinability, and also you want to be able to easily modify it um, to insert your thermistors and heaters and things like that. You also may want to make sure that the material can take some heat. Okay. Um, I think most materials will be fine because you're only providing a 9-watt heater, so the material should be insulate, be a good insulator. It should have be machinable. Um, it should be um, able to take some heat, so heat stable. Okay, things like that. And you can think of other reasonings in selecting the material. Right? Okay, and um, you also should figure out a good barrier material, which is some kind of foil, metal foil that will touch the cup. You could also use a combination of materials. You don't have to use just one material. You can have one layer of one insulation, another layer of another insulation. So multiple insulations, multiple barrier materials, all of them are fine as long as you um, constrain it to the outer dimensions. Okay, the design constraints are satisfied. So material selection, then you have to figure out how to create this 3D model, because if you think about it, if you have something like this, you have to figure out where to put the heater. So maybe you want heater here, here, maybe you want the thermistor here, or you have thermistor. So you provide a CAD model to show how you plan to pass the heater. So you have to take the wire through here, or the heater wires through here. How does it come out? Things like that. Okay. So when you actually create a CAD design, you will realize some new problems. So that's why a CAD geometric design, um, it doesn't have to be finalized. Have something started, um, and if you finalize it, that's great. But you can change it. It doesn't. You don't have to stick to the design that you present in midterm. You can always change it later on. But the goal is to make sure that you are in the right track. Okay. If your track is not right, this midterm presentation is to help you to go in the right direction. The heater and thermistor placement, of course, I just mentioned that. That has to be done carefully. If the heater is exactly on the thermistor, then the thermistor will um, read a very high temperature, right? Um, if the heater is right on the thermistor. So, and instead of measuring the temperature here, it will be very highly inaccurate because it was very corrupted by the temperature from the heater. So you have to probably locate the heater and thermistor in such a way that they are not um, making the measurements wrong of the beverage. Okay. The other thing is you have to ensure that there is good thermal contact. Okay, you have to enhance the thermal contact. What do I mean by that? When the cup is placed and you have a lot of gaps, for example, okay, and your thermistor is here, it's not going to read the temperature of this water if there is a lot of gap here. It needs good contact to the surface, and the thermistor needs to connect very well to that surface for it to measure accurately. Same thing goes for heater. Okay, if there is a lot of gap here, the heat from the heater will not directly go to um, the surface of the cup. So good thermal contact. Figure out a way how to make sure that everything presses up against the um, cup and measures the temperature correctly. So I want to see, or we want to see your thoughts on this. The thermistor calibration portion you have already performed during the demonstration, but if if you're thinking of improvements in how to make sure that your thermistor is calibrated better, also you have a second thermistor. How you plan to calibrate the second thermistor, because you'll need both of them to design your um, setup for the final exam. And I will get to that in a minute. The You could also talk about the control logic that you plan to use to maintain the beverage temperature. And what I mean by beverage temperature is the center temperature of the beverage. Okay. Um, so we'll measure the center temperature of the beverage, um, of the water in the cup. Okay. So you have to figure out how do you plan to control that? How do you plan to figure out cut in and cut out temperatures? Um, if you plan to figure out the cut in and cut out temperatures, you don't really need the offset. Okay, it depends on how you plan to use it. Um, if you're using cut in and cut off temperature as 54 and 56, then all you need is an offset at that point. Um, Heater on off logic, LED status indicator logic, etc. Okay, how you plan to uh, do that? We don't need to show any codes. No codes to be shown. Okay, so all of this is to gauge your understanding. Um, this examination. Okay, there is no results to be shown as such. Then, of course, you can talk about how you plan to put the LED indicators, where exactly you want to install them. Then about how you plan to design the circuit. You should have some kind of box which you can easily connect it to a power supply and your laptop. And the warmer should be located separately from that box, maybe by a cable length of roughly 1.5 meters or longer. Okay, so you could basically talk about these things on your midterm presentation. The cut in and cut out temperature selection is important for your final exam. And what do I mean by that? So you were given two thermistors. Okay, you had two similar thermistors that were given to you during the hardware distribution. One thermistor, of course, you will use for your final exam. The other thermistor you would use to make sure your code is working right. Okay, so you'd connect both of them to Arduino or your Uno, and um, you'll measure both of them and try to energize the heater and look at the water temperatures. One thing to note here is because they are located at two different locations, the temperature at this location, let's call this as location 1, and this is the location 2. You're graded or you're tested based on this location, which is the center location, okay, of your beverage. So the temperature here is what we are interested in. Somebody who's drinking from this cup, they are going to drink the fluid inside it or the beverage inside it. So that's the temperature they are interested in. The temperature here may be much higher or lower depending on how you have installed the thermistor, right? So the green line here represents the temperature of thermistor 1 at location 1, and the purple line here represents the temperature in the center. So you would basically turn your heater on and off and see how your um, control of this temperature, this thermistor, affects the control here. So let's say these two lines, the low and the high, are two temperatures that you've decided, and I'm gonna randomly pick two numbers here. Maybe you had to pick this one at 55 C, and this one you had to choose 57.5 C, okay? And then with between that, when you control that between that, you turn off your heater, turn on the heater and turn off the heater based on these two cut in and cut out temperatures, okay? Um, so cut in means that's the temperature at which the heater will turn on, and cut out is when the heater will turn off. So you fix this at this condition, then you're able to get your center temperature, between 54 and 56. Okay, so that's the importance of figuring out the cut in and cut out temperature. It will change if you move the thermistor somewhere else, something else will happen. Okay, and if the thermistor is not contacting the cup well, this this might not work either. So it is very important you have good thermal contact and you design everything correctly. And when you come for testing, your cut in and cut out temperatures still are the same, and it'll control correctly to make sure that the purple data or the center data is between 54 and 56. Okay, so if you do all the testing in your lab and develop all this, but your design is not robust, and if the thermistor moves around and you come for the final test, then you will have a problem. Okay, so make sure the thermal contact is the same on the last day of your test and also when you're developing these um, cut in and cut out temperatures. Okay, and you may have to do a trial and error to figure out how to move these two lines, okay, this line and this line, to make sure this is within that. It's okay if it's not going to touch this. I'm also okay if your purple line looks something like this. Okay, if it's inside 56 and 54, that's all that matters. Okay, and you could, instead of the using the thermistor number 2, you could use your own sensor. If you have a fluke meter or something, you can put a sensor in the center and you can measure it that way too. Okay, but it will be best to use I wouldn't say it's best. You could choose another measurement system in here to make sure that it's not moving. It's exactly the right temperature at the center. Okay, it doesn't have to be this thermistor, but you have at least two thermistors, so you should be good to use that if you choose to. All right. Now about the final exam, there are three sets of goals. The first goal was temperature control. The first goal is temperature control. The test is to evaluate the performance at roughly room temperature of 25 degrees C. When you bring your setup, the first thing we'll do is we'll measure the dimensions of your warmer and the heat of the warmer, external dimensions, the diameter and the height. Then we'll also measure the heater resistance to make sure everybody's heater resistance is within the right range. Okay. Then we'll place the cups into the warmer and uh, making sure that the warmer is not hot already. You shouldn't turn on the warmer right before the test because that will give you an unfair advantage. Um, the warmer should be all at room temperatures before the test starts, right? Um, then we'll put a new temperature sensor, a reference sensor, and we'll measure the center temperature of the beverage. Um, and hot beverage, it'll be water, not tea. We'll bring hot water at temperature slightly above 60 degrees C, and we'll pour roughly 275 ml. Okay, this will be 275 ml of water. So during your practice test, you can pour 275 ml of hot water, heat it in a microwave, and pour it in a cup and test your system, right? Um, Test duration will be roughly 2.5 hours. So once your test starts, we'll see how your temperature goes for 2.5 hours. Everybody's will be tested at the same time. Okay, and you'll be evaluated based on your average temperatures. What is your average temperature, min and max temperatures? How many times, whether you go outside of this or if you go outside of this, above or below, you might it might affect your score. Okay, and how well your LED's status is working. All right. So the LED status basically is there are two LEDs. The red LED should turn on or off when the heater is on or when the heater is off, right? When the heater is on, it should be on. When the heater is off, it should be off. And the green LED is whenever your temperature is between 54 and 56 degrees, it should be green. And whenever it's outside of that, it should be off. Okay. All right. Goal number two is thermal efficiency. So this is just the temperature control. Thermal efficiency is how much of the heat that your heater is generating is going to the water, right? If you if you install the heater correctly and if you chose the material, insulation material correctly, most of the heat will be going to the water, right? So if you have a cup here and you had an insulated material and you put the heater in the right location, so there's heat going to the water and then there's heat being lost, right? So basically the efficiency is heat going to the water divided by heat going to the water plus heat lost, or the total heat. That's what we are looking at. So the better insulation you have, the better installation of heater you have, the better heat transfer to the water, right? So and the better design of this insulation. So you can design this insulation such that, okay, there is a limitation in height, right? You could design it such that you put all the insulation in the bottom, right? Somebody could design such that uh, the insulation is more on the not a lot of insulation on the bottom, more insulation on the sides. See, depending on that design also, um, and there could be leaking through the wires, so heat losses through the holes for the wires. All of that will mean that your efficiency is reduced. So to test this, you have to make sure that the heater is running continuously, right? Heater is on continuously. So you cannot use your logic, right? You cannot use your logic. So I don't want you to write another logic. What we'll do is we'll modify the heater connection to bypass the relay, okay? And the heater will be energized continuously by the power supply. And we'll, for half an hour, we'll see what is the temperature change. Uh, and then depending on that temperature change, we'll look at the efficiency, okay? Now, some more details for the final exam. Your heater wire, unfortunately, we couldn't find um, silicone wires with nichrome heaters inside. Instead, what we have is PTFE insulation and carbon fiber heating elements. Okay, um, the resistance that I measured for most of these are in the 59.5 ohm region for each of these four strands, and all of them are roughly 18 inches long. Um, so if you connect all four of them parallel, you should get 1/4 of this resistance. Okay, somewhere close to um, 15 ohms or 15 to 16 ohms. Okay, um, so because it's a carbon fiber heater, do not solder using the typical soldering gun. Okay, there are some special solders that are used, which I don't want you to buy for this project. Instead, you can buy some simple connectors or pick up some connectors from the lab or in the mechanical engineering department and use a mechanical connection method, mechanical crimping method to connect these heaters. And these heaters have to be connected in parallel. Okay, so the resistance is 1/4 of the resistance uh, of each of them. Okay, so 1/4 of roughly 59.5. So connect them in series, parallel like that. Now you can have one heater cable going like this. You can have another heater cable here, another one here. In the end, all of them just have to be connected in parallel. Okay, so you can, this connection, you can have any length, but the heater length has to be the same. So you can, this has to be 18 inches, right? You can have connecting wires that are longer, but in the end, I will measure the resistance here, okay, and make sure that that resistance is close to R by 4. where R is this. So that's a check we'll do before your um, final exam. Now, relay board details. The relay, this particular relay doesn't show which is normally open, normally closed. So I've shown you which one is normally open, which one is normally closed, what is the common. So you have to figure out where to connect these by searching the internet. Okay, that's how you learn how to use a relay. And you should also try to figure out what is a relay. And there are two relays in this. Okay, you only need to use one relay. Only use one relay. Okay, and the other thing to remember is you have to have some special connectors. Um, these connectors should be between the location C and D and A and B. Okay, so what are these locations? These are the four heaters. These are the heaters connected in parallel. Heaters connected in parallel. And you have the power supply. Power supply is connected to the one end of the power supply is connected to the relay. And only when the Arduino tells you to power it will this send power. Okay, it's like a switch inside. So it's normally not connected, but when the Arduino tells it to send power, it will connect. You should have a wire that is spliced into this wire and a wire that is spliced into this wire, and we should be able to quickly connect this for the second test. Okay, and for this side we should be able to disconnect this also. So use quickly removable connectors like these, any of these, at this location and this location. Okay, for normal testing this will be connected. AB is always connected except for resistance measurement, and CD is disconnected always except during test number 2. During test number 2 you'll connect this and bypass the relay. Okay, so some types of connectors are shown here which we can quickly open and close and connect. So use any of those that you can find. So what is resistance measurement? So this will be done before the final test, and the resistance will be measured between B and D to check whether the resistance is somewhere between these values. Okay, um, and once that resistance is measurement is completed, we'll connect this back. Okay, and then you can do your first test. Before the final test number 2, where you're testing the thermal efficiency, you'll connect C and D. Okay, now all the power is going through the resistor, to the heaters from the power supply. So the resistor on off here does not matter. Okay, so you will be continuously heating. So this we'll do right before the second test where we are trying to measure the thermal efficiency. All right. So for the final exam, your test setups should look something like this. A lot of these things should be inside a control box. Okay. And you should have cable length of roughly 1.5 meters that goes to your warmer, cup warmer. And it should have cables coming from the relay going to the heaters and also from the power supply, then cables coming from the Arduino to connect to the thermistor and also to the LED indicators, etc. And you should also have a laptop to monitor your data. You should have all the data shown on the serial monitor. Okay, you should look at the heater status on the monitor, LED status, um, and the thermistor reading on your serial monitor. Okay. All right. So I think that's most of the details that you need for preparing for the final exam. One thing or some things to think about as you go along with this project is, okay, what is a relay? Why do we need a relay to control the heater? Why cannot we directly control the heater using Arduino? After going through this exercise, going through this projects, what new things have I learned, and how can I use it for my other projects or future? Is the warmer design safe? If not, how can we improve? We are using a heater. What happens if that heater never turns off? So is it safe? How much energy does this design consume for maintaining temperature for few hours, for example, 2 hours, right? How many joules or how many watt hours does it consume? Based on that, if you use a battery to power the cup warmer, um, how many hours will it maintain temperature before recharging or replacing? What are some better materials to use to minimize the size of the warmer? Okay, and how can we improve this design to use different cup sizes at the same time not consuming a lot of energy, right? So some of these questions you should think about. All right. So I hope this clarifies a lot of questions you may have. If you have more questions, you can reach out to me or other professors who are in charge of this course. Thank you.